Have you ever stopped and really thought about how your data gets from your screen to, well, literally anywhere else on the planet? I mean, we stream movies, we send huge files, we share stuff across the globe in a heartbeat. But underneath that super smooth experience is one of the most complex, coordinated systems ever built. So today, let's pull back the curtain and explain how it all actually works.
So let's start with a really simple question, right? You see a hilarious cat video, you're in New York, you hit share, and your friend in Tokyo is laughing at it almost instantly. What just happened? What's the secret sauce? How did that digital cat just travel across the Pacific Ocean faster than a 747?
Well, the short answer is it travels through this absolutely massive, mind-bogglingly complex system. We're talking about a global web of countless devices, hosts, routers, those giant fiber optic tables under the sea, and a whole rulebook of protocols that tell everything how to talk to each other. It really does sound like total chaos. And you know what? In a way, it is. But there is a beautiful method to this madness.
So how in the world do you tame that? How do you build a system that you can rely on out of so many different, independent, moving parts? Well, the folks who designed the internet came up with a really elegant solution: layering.
I want you to think of it kind of like a factory assembly line, but for your data. This whole process is called encapsulation, and it's all about breaking down the massive, complicated job of sending information into a series of smaller, much easier to handle steps.
To really get a grip on this, let's use an analogy. Air travel. You don't just walk up to an airport and fly a plane, right? No, it's a series of layers. First, the ticketing layer handles your purchase. Then, the baggage service layer takes your bags. Then, the gate agents handle boarding. Each layer does its own specific job, and it provides a service to the layer above it without needing to know all the tiny details of what the other layers are doing. And guess what? The internet works the exact same way with what we call its protocol stack. Up at the very top, you've got the application layer. That's your web browser, your email client. Below that, the transport layer manages the end-to-end connection. The network layer figures out the best route across the country, or the world. The link layer handles just the next hop to the very next router. And finally, the physical layer turns it all into actual electrical signals on a wire. Pretty neat, huh?
Okay, so this is the key. Encapsulation is the process of passing your data down through all those layers. And at each stop on the assembly line, it gets wrapped in a little bit of extra information. We call it a header that specific layer needs to do its job. It's just like putting a letter in an envelope and then putting that envelope into a bigger shipping box.
Let's actually watch this happen. It all starts with your original data. That cat video, that message you're sending, we'll just call it M for message. This is the raw stuff coming from your app.
So first, your message, M, gets passed down to the transport layer. This layer slaps on its own wrapper a transport header, or H. This little header has info like port numbers, which is crucial because it tells the receiving computer which specific app should get this message. You know, so your cat video doesn't accidentally end up in your friend's budgeting spreadsheet. Right, so then that whole package gets handed down to the network layer. And what does it do? It adds another header, HN, which contains the big stuff, the global source and destination IP addresses. This is like the main mailing address for the entire journey from New York to Tokyo.
And at the very end of the line, this package arrives at the link layer. It wraps everything in one final header, HL. This one's just the local address for the very next stop on the network. This fully wrapped package is now called a frame, and it's finally ready to hit the road, or, the physical wires.
Okay, so our data is perfectly packaged up. It's addressed like a set of Russian nesting dolls. But what about the actual delivery service? I mean, how do we physically move these packages across the network? Well, historically, there have been two really big ideas, two competing philosophies on how to get this done.
So on one side, you've got circuit switching. I want you to think of this as chartering a private jet. It's a direct, dedicated, private connection from point A to point B. That entire flight path is reserved just for you and nobody else can use it. Then, on the other side, you have packet switching. This is way more like a convoy of cars. You break your cargo up into a ton of small cars and each one independently finds its own way through traffic to get to the final destination.
So, the private jet versus the convoy of cars. They're fundamentally different approaches, right? So, let's dive in a little deeper now. Let's look at the technical details and see what really makes these two methods tick.
So circuit switching is the old school model. Think about the original telephone system. When you made a call, a physical circuit, a line, was literally opened up and kept open just for you two for that entire conversation. Your voice traveled as one single continuous stream along that one dedicated path.
Packet switching, though, is a whole different ballgame. This is the engine that powers the modern internet. Your big message, that cat video, gets chopped up into hundreds or thousands of smaller, manageable chunks called packets. Each one of these little guys gets its own address label and is then sent out into the wild network to basically fend for itself.
So let's put them head to head. That private jet, circuit switching, it guarantees your data arrives in perfect order, which is nice, but it is incredibly inefficient. You're reserving the entire highway even when you're not talking. And its fault tolerance, it's really low. If that one path breaks, your connection is just dead. Now, the convoy of cars, packet switching, is way more efficient. Everyone shares the road as needed. And this is its killer feature, fault tolerance. If some construction crew accidentally cuts a fiber cable under the Atlantic, your video call doesn't just drop. No way. The packets just instantly find a new path around the problem. The trade-off, of course, is that it's more complex, and sometimes the packets can arrive out of order.
So given those trade-offs, one method is simple and orderly but fragile and wasteful. The other is chaotic and complex but efficient and tough. Which one did the architects of the internet choose? Well, you're using the answer right this very second.
Packet switching won, and it wasn't even close, and it won for some really powerful reasons. It's just so much more efficient with the network's resources. It's more reliable because the destination can spot if a packet is missing and just ask for it to be sent again. It is way, way more fault tolerant because it can just route around problems. And all of this, taken together, makes it unbelievably cost-effective to build and scale a network that covers the entire planet.
But, and there's always a but, right? This incredible flexibility isn't free. The very thing that makes it so powerful, sending millions of individual packets through this congested, constantly changing network, it introduces its own set of problems. And the biggest one is delay.
So what kind of delays are we talking about? Well, there are four main culprits. First, you've got transmission delay. That's just the physical time it takes to push all the bits of your packet onto the wire. Then there's propagation delay, the time it takes to travel the actual distance. Then there's queuing delay. This is what we feel as lag. It's your packet getting stuck in a traffic jam in a busy router. And finally, processing delay is that tiny fraction of a second a router takes to read the address on your packet and figure out where to send it next.
And this all leads to what I think is the most important takeaway here. The internet was never designed to be neat and tidy. It was designed to be resilient. That seemingly chaotic nature of packet switching, of breaking data up, sending it on all these crazy journeys, and putting it back together at the end, that's not a bug. It's a feature. It is the absolute secret sauce that makes the entire global network so incredibly robust and scalable.
And that leaves us with one final thought. This packet-switched convoy of cars model has powered our digital world for decades. It's been amazing. But as our demands just keep growing, we're talking lag-free cloud gaming, fully immersive virtual realities, will this model be enough? Or will the future of the digital highway require a completely new way to travel? Something to think about.